All right, hey everybody. So today we're going to be doing 3-2 measures of variation. Okay, so we have the key concept. Variation is the single most important topic in statistics. So this is the single most important section in this book. This section represents three important measures of variation: range, standard deviation, and variance. And when we talk about variation, we're trying to figure out like what our values are. Are they really closely tied together? Are they all over the place? For example, let's talk about heights of the population of men, right? They don't vary that much. They may vary by, maybe 6 inches at most between, in general. Now we have people that are not very tall, and we have people that are very tall. Those are at the edges of our numbers, but I would say probably most people are in a certain range, right? And that's what we're going to talk about. These statistics are numbers, but our focus is not just computing those numbers, but developing the ability to interpret and understand them. Okay, so that's very important. When we want to talk about the range, we're basically talking about, we have these values that are in our data, right? And if we have a sample, we just have a smaller set of values. If we take the whole population, we have a very large set of values, right? But the range basically just means the maximum value minus the minimum value. And we'll do some problems. I'll show you how to find it. Okay, so like here, for example, say we have these values, right? And we want to find the range. So we find the biggest value, and that's not what so our largest value would be 55.6. And our smallest value is 14.1. We subtract those two values and we get our range. That's really all there is to it. It tells us a lot of information. And if you remember from last week, from the last lectures, remember we talked about things that are resistant. Would you say range is a resistant value? Think about it for a second. If I had one outlier, let's say also here I had 1,000, right? Now my maximum value minus my minimum value is way different than this number, right? It would be 1,000 minus 14. So it is not a resistant value. It is very important what the numbers are, right? Okay, standard deviation of a sample. So the standard deviation of a sample, a set of sample values, which is denoted by small s. So the notation is small s means we're taking a sample, and this is a Greek letter called sigma, and it represents the standard deviation for the entire population. Okay, and it's a measure of how much data values deviate away from the mean. So, for example, we're gonna learn about bell curves today. But let's say we have a bell curve that looks like this, right? And in the middle of the bell curve, we always have the mean. So if this is our bell curve, then we can see that the data is spread out a little bit. But if I take that same if I take the same shape and I draw it just a little different, like what if our shape looks like a bell curve that looks like this, right? Well, the mean is still right in the middle, but notice most of our values are very much closer to the mean than they were with this other smaller, shorter graph, right? So we might have the same amount of data. It keeps disappearing. So we might have the same amount of data in here, in this red area, as in this blue area, right? It's just arranged different. So we would say that the red bell curve would have a smaller standard deviation than the blue because they're going to deviate more. Okay, they're not as close to the mean. Actually, I was going to show you how to do this. Here, let's go back to here. Let me get our, let's see. No, I'll do it all together. I have a few of them. So calculating the standard deviation, I'm going to show you here how to calculate the standard deviation, and we're not going to do these calculations. We're going to use StatCrunch, but I do want you to understand how we're getting these values and where they're coming from. And basically what this means, I know that these formulas look crazy, but what it means is if we know, it's telling us here that our mean is 30.7. It's a sample mean, that's why it's X bar, right? And what we would do here is we would, remember this means to sum. So we would add up X minus X bar. These are my X values. So I would say this would be the same as saying 38.5 minus X bar is 30.7. And then we square it. Plus 55.6 minus 30.7 squared. Plus 22.4 minus 30.7 squared. Plus 14.1 minus 30.7 squared, plus 23.1 minus 30.7 squared. So that is basically, if you do all this work, you should get this value. And then we're going to divide by n minus 1, where n is the number of values. So I have 5 values here. 1, 2, 3, 4, 5. So n minus 1 would be 4. So we would take all these numbers and we would divide by 4, which is what they're saying here. We would then take the square root and we would get our standard deviation. Now, we're not going to do that, okay? But that, I just want you to see that really what you're finding here is the distance away, the distance this data is away from the mean. And you're squaring it because that makes it positive. Because some of these would be positive and some of them would be negative. So they would add and subtract from each other. So we square them all and then we take the square root, okay? So of a population, it's a little different formula, not much, but when we're talking about the entire population, then instead of dividing by n minus 1, that 1 won't make much of a difference because we're talking huge amounts of numbers in a population. So we're just dividing by this capital N, which is the number of people in the population. We're using sigma instead of S for standard deviation because it's the population. And here we're just summing all the values minus the mean. Mu is the mean for the population, and we square it. It's really very similar to the other one, except now we're using much more data values. So we have this range rule of thumb to identify significant values. So what this is doing is basically we're let me arrange a little bit different than I may want to arrange it. So range rule for estimating the standard deviation. And what we do is we say, we find the range and divide it by 4. And that we can say is an estimate of the standard deviation, because we may not want to go through all that work of getting each value and subtracting it. And maybe we don't have a good technology that could get us there real quickly. So we can just take whatever the range is, divide it by 4, and we can say this is a rough estimate. Okay, now let's look at this picture because it's important. Here is my mean, and here is one standard deviation away. And this is actually 2 standard deviations. That's why it's saying it's the mean plus 2 standard deviations and the mean minus 2 standard deviations. Okay, I should probably erase what I just wrote because I don't have room to fit. But that would be mu plus 1 standard deviation, mu minus 1 standard deviation. And basically what this says is that all the values in here are really not significant. We can go up or down a little bit without it being really out of the values that we would expect. But once we get out this way and this way, so more than 2 standard deviations or less than 2 standard deviations away from the mean, we're talking about things that are significant, that they don't just happen by accident, that they're really, they're very, how could I say it? That they mean something, that they're significant. So if I said that the average height of a male is 5'11", 5 feet 11 inches, and I found that I had somebody who was 7 feet 2 inches, that would probably be way out here in the significantly high values. Okay, so we want to really look at, sometimes we want to look at if it's significantly high or significantly low. We might find somebody who's 3 feet 6 inches tall. That would be significantly low value. Okay, so that's basically what this means. Hopefully that makes sense. And then we have variance, and I'm going to do some problems in a minute. Variance of a sample and a population. So the variance of a set of value is the measure of the variation, which is equal to the square of the standard deviation. So if you have a standard deviation, you square it, and that's your variance. When it's for a sample, we use standard deviation as S, and then we square it. For a population, we use sigma, and we square it. That's all that this is doing, is taking those values and squaring them. And here's the notation. So S for sample standard deviation, S squared for sample variance, sigma for population standard deviation, sigma squared for population variance. And I think, where is it that I want to do? Yeah, so let's read this and then we'll do a problem. So, no, actually, I'm not going to, yeah, I'll read this. So comparing variations in different samples or populations. So it is a good practice to compare 2 sample standard deviations only when the sample means are approximately the same. Okay, so compare only when the sample means are approximately the same. So when comparing variation in samples or populations with different means, it is better to use what we call the coefficient of variation. Also, we use the coefficient of variation to compare variation from 2 samples or populations with different scales or units. So what that means is, so different scales or units of values. What if we wanted to compare miles per gallon to weight of a car? So if I did that, I could say the units for gasoline consumption, right, would be miles per gallon. The units for weight of a car, maybe it's pounds, right? Depends on how you measure it. So these are called units. Miles per gallon is units, pounds is units. If we're going to compare things that have different scales or units of measure, then we would again be more likely to use this coefficient of variation. Oh, I guess they give us such as a comparison of variation of heights with men with heights of women. Again, they're going to be different, even though they have the same units. So here is the formula, and we're not going to really use the formula. More than we're going to use StatCrunch. And now I am going to let's bring over some problems that I found for us. Okay, so question 1. Listed below are prices in dollars for one night at different hotels in a certain region. The range, variance, and standard deviation for the given sample date, we're going to find those. Include appropriate units. We talked about units and the results, and how useful are the measures of variation for someone searching for a room. So notice I have my box here that I click on, and I'm going to open this in StatCrunch. And I'm going to put that on one side. I'm going to put this on the other side. And let's get rid of all these numbers. Oh, no, these are the numbers. Sorry, we're not getting rid of those numbers. So we just got the numbers from this problem. And now I want to find the range. Here, let's say what we want to find. We want to find the range, the variance, and the standard deviation. So I'm going to click here to Stat, Summary Stats column. Select bar 1. And I always liked, I don't know why, I always like to have the number. I need the variance. I need the standard deviation. And I'm holding down the control key. When I do the first number, I don't. Then as I want to add more and more variables, I hold the control key down, and then more than one will go in. Standard deviation. And we want the range. And let's do min and max so we can see how the range is being calculated. And I think that will do it. So let's compute. And now I have all my information. So the range, and the reason I wanted to do this is because I wanted to show you that, I wanted to show you that if I have my max minus my min, or actually, let me do it like this. I get 8,6,168, right? Which is exactly what it's giving me here for my range. I don't need to do the math, but I wanted to show you that that's all that they're doing, okay? So let's put in our number. So the range is 168, and here they want to know what the units are. So it's 168, and here it says listed below are prices in dollars. So it's $168. Let's check the answer. Perfect. The standard deviation of the sample data is, I can copy it, and we want to do it to one decimal place. So we're going to have to round that to a 3 because the number after the 2 is an 8. So this actually gets rounded up to a 3, and our standard deviation is in dollars. Perfect. And then the variance, which is the standard deviation squared. So I have, let's copy it. And we want this to 1 decimal place. And the 8 is next. So that means I'm going to have to make that last number is going to be 0.8 instead of 0.7. So let's round it up. And because the variance is the standard deviation squared, what our units are going to be is dollars squared. Okay. And then we're going to see how useful are the measures of variation for someone searching for a room. So the measures of variation are not very useful because when searching for a room, low prices, location, and good accommodations are more important than the amount of variation in the area. So basically it's saying that, yes, there might be there's a range of $168 between the cheapest room I can find and the most expensive room I can find. But we're not talking about how good those hotels are. Some of them are not good hotels and some of them are better hotels, right? So we know that depending on the quality and the level of the hotel that we're staying at, that it could be different. So I'm going to say A, but let's read them all so we can see whether or not they make any sense. The measures of variation are not very useful because the values are nominal data. So remember what nominal data was. Nominal data was values that you could put in order, but they didn't represent counts of anything. And dollars definitely represent counts. So nominal data is not the answer. This is not nominal data. This is actually values that have meaning. Nominal would be more like the letters on the back, the numbers on the back of a football player's shirt. They're numbers, but subtracting 2 of them or adding 2 of them or taking the average doesn't make any difference, right? The measures of variation are very useful because a person does not want to buy a room where the variation is too high. Well, I don't think that's true because we all know that different hotels are going to charge different prices. We may not want the most expensive, but we may not want the cheapest. And the measure of variation are very useful because a person does not want to buy a room where the variation is too low. Nothing to do with picking a hotel, right? So I think it's A. Let's check. Okay, we got it. So there we have it. I wanted to show you how to look at StatCrunch, how StatCrunch can help you. Okay, so it says the coefficient of variation for the pulse rates is, actually, let's read the whole question. I'm going to open it full screen. So listed below are pulse rates from samples of adult male and females. Does there appear to be a difference? Find the coefficient of variation for each of the 2 samples, then compare the variation. Okay. So I'm clicking on the box, I'm opening it in StatCrunch. Put that on that side, I'll put this on this side. And we're going to go summary stats columns. And we're going to pick both. I'm going to hold down the control key to get the second one. Again, what do I need? The coefficient of variation. I think there it is. So there's my coefficient of variation. And that's really all I need. There's my data. And it says the coefficient of variation for male pulse rates is, and this is giving values in percents. So for males, and we want to round it to 1 decimal, so 17.3%. Check. Perfect. The coefficient of variation for females is 10.3 to 1 decimal place, 10.3. Check our answer. Perfect. And now it wants us to compare them. The coefficients of variations for each data set are more than 5 percentage points apart. They're 7 percentage points apart, right? 17.3 minus 10.3. They're more than 5. Therefore, the male pulse rates vary significantly more than the female pulse rates. So there's more variation in male pulse rates than in female pulse rates. Because obviously, if it was less than 5 points, we could say we would choose about the same. But there's more than 5 points. That's a big difference. And we check our answer. And I think the last one we're going to save. Actually, we can do this one. This is by the rule of thumb estimate. And if you remember how to do the rule of thumb estimate, actually, we don't use StatCrunch for that. That is something we have to do in, so using the rule of thumb, the standard deviation is approximately what? Well, actually, we do need StatCrunch because we have to find. So let's open this in StatCrunch. Move that over here. And let me close this. So the rule of thumb law, hold on, let me get my pen. So the rule of thumb we want to find the range. So S is approximately the range divided by 4. Okay. And notice how hard it is really to find the range because we have so many numbers. Like we don't want to look through all these numbers, do we? So instead of doing that, we're just going to go here to summary stats columns and var1. And really all we need here is the range, which I guess I missed. There it is. So all we really need is the range. We hit compute. The range is 5. So this is equal to 5 divided by 4. And in decimal, that's 1.25. If you're not sure how to do that, you would do 5 divided by 4 on your calculator. Okay. And so it's approximately 1.25. Oh, I did it wrong. So let's see. Standard deviation. Type an integer or a decimal rounded to 1 decimal. Oh, I didn't round it to 1 decimal place. See, that's my fault. 3. Check answer. Now it's correct. Okay, compare the result to the actual standard deviation. Okay, so I can just go right back up here and hit options, edit. Here, let me erase all that stuff I have. Okay, so I need the standard deviation. Now they're asking me about the real standard deviation. We can put the standard deviation and the range both together. And then I hit compute, and now I have both pieces of information. So the estimated standard deviation is, well, estimated, if I rounded to 1 decimal place, would be 1.3. So it is within 0.3 of the actual standard deviation. Thus, the estimated standard deviation is not significantly different than the actual standard deviation. It's actually pretty much exactly the same. If I rounded this to 2 decimal places, I would have 1.3. And those are the 3 questions that I did pick out for us to do for this part of the course. Okay. Now we're going to look at the empirical rule for data with a bell-shaped distribution. This is very important. You will need this information. So if I were to draw a bell curve, actually there's a picture coming up in a minute that'll be a lot nicer than mine. Remember, we have here in the middle is the mean. And if I say that this is one standard deviation, and we'll call this, we'll call it mu, it could be X bar, depending on if it's the sample or the population. This would be mu minus one standard deviation. And this would be mu plus one standard deviation. Okay. And what they're saying here is that 68% of all my data is going to lie in here within one standard deviation. Okay, so this is 68%. If I pick another value, if I want to find two standard deviations, 95%, let's say this is 95%, and that would be two standard deviations. And then if I go to three standard deviations, this is three standard deviations. And they're going both directions, right? Three standard deviations. That means 99.7% of all our data is within three standard deviations. So these are the important numbers: 68, 95, 99.7. Okay. And here's the nicer picture. These are more exact. So 34.13% lie to this side and 34.13 lie on this side. So if I add it together, it's 68.26. So we're estimating it at 68%. Okay, that's within one standard deviation. Two standard deviations, we add on more, and that's about 95%. And three standard deviations goes all the way out here. Look how small what's left is. There's just a little tiny bit on both sides. And that little tiny bit, so if I remember under this entire curve, so we have 1. So if I add up all the percentages, I have 100%. Probabilities always go from 0 to 1. So that would be the same as 1 probability. Okay, so under this entire curve is 1. Basically, since this is the middle right here, 50% lies to the left and 50% lies to the right. So 0.5 and 0.5, right? And what else do I want to say about this? Oh, if I want to find out what is more than 3 standard deviations away, I could say 1 minus 99.7, which is equal to, actually, it would be 100 because, hold on, because this is in percentages. So this would be not 1, but 100, which is equal to 0.3%, which is equal to, so that means that half of that, so 0.3 over 2, oh, I can't write down there, sorry, divided by 2 is equal to 0.15. So 0.15% basically is outside of 3 standard deviations, which is pretty close. We're just estimating. It's really 0.13. Okay, so hopefully this chart makes sense to you. We do need this chart. So for example, IQ scores have a bell-shaped distribution. Okay, let's draw a picture. Okay, with a mean of 100. That means in the middle here, we have 100 and a standard deviation of 15. So let's say this is one standard deviation. This would be 100 plus 15, which is 115. And on this side, we would have 100 minus 15, which is 85. So what are we saying? 68% of all people, if you look at their IQ score, is between here and here. This is one standard deviation away from the mean. Okay, but those aren't the numbers that I'm looking for. So if I did it again, we would find it. But what I want to do is I want to show you how to find it if you like, if it's not exact. So I could say we could do it to either one. So if I have 100 minus 70, that equals 30. So that's the difference between the value. So this is X bar minus, minus X. So X bar minus X. And that is 100 minus 70. And the other way, we have X minus X bar because we really just want it to be a positive value. You could say the absolute value as well. You could just take the absolute value and make it X minus X bar for both. So this would be the absolute value of 130 minus 100, which is also 30. So we're 30 away from the mean on both sides. What we want to do is take our mean and divide it by our standard deviation. So we have no, that's not what I want to do. Sorry. I want our mean. I'll say the absolute value of the mean minus X, or X bar minus, let's do it this way. I don't mean to make you crazy. So this is 30, and our standard deviation is given right here, is 15. So that gives me 2. This is 2 standard deviations from the mean, right? Because if I do another 15, I would be out here and out here. And if I add 15 more, I'd be 130. If I subtract 15 more, I'd be at 70. So 2 standard deviations. That means what we want to know is how much data is between these 2 numbers. And using the empirical formula, we know it's 95%. I'll show you in a second. So this is 95% of all our data lies in that yellow part. And that's coming from here. So X bar minus 2 standard deviations, X bar plus 2 standard deviations, and we go up here and we can see 95% of all data lies within 2 standard deviations. Okay, so that's basically what we're looking for here. This is just the way they're doing it. And that really is the end of this lecture. There's really not much more for me to talk about here. So if you have any questions, of course, always you can ask. Otherwise, have a great day. Bye-bye.